In this module, you will learn about fundamental concepts and basic laws of Boolean algebra, Boolean expressions and how to generate them, the basic operations used in computers and other digital circuits, representing Boolean logic problems as truth table, how logic relates to computing problems. George Boole, an English mathematician, introduced the concept of Boolean algebra in 1854. He was mainly working on differential equations and the calculus of variations. However, he is familiarly known for his work on application of algebraic systems to non-mathematical reasoning. He came up with the proposition that logical propositions should be expressed as algebraic equations, due to which logic was reduced to algebra. In all his logical deductions, the multiplication operation was replaced by and addition operation by or. But Claude Shannon's work on using Boolean algebra to design switching circuits in late 1930s became the foundation of computer logic and design. According to Boolean algebra, things are mapped into bits and bytes. Due to this, we can find its applications in telephone switching circuits, in the hardware and software applications of computers. Thus, Boolean algebra plays an important role as a tool for analyzing, designing, and implementing digital circuits. It is an algebra of two values, like true or false, or yes or no, or 0 or 1. Let us now learn about the components of Boolean algebra. Boolean algebra is made up of elements, operators, axioms, and theories. Elements are variables or constants with value 1 or 0. The operators in Boolean algebra are and, or, and not. A symbol used to represent a logical quantity is called a Boolean variable. This Boolean variable takes value from the domain 0 to 1. Similarly, a Boolean constant is a single-digit binary value like 0 or 1, which is otherwise called a bit. The three primary operators are and, or, and not. The binary operator and is used to perform logical multiplication. It is represented by a dot. Or is another binary operator which is used to perform logical addition and is represented with the help of a plus symbol. Not is a unary operator which is used to complement the operand. Take a look at the screen to understand how it is represented. The inverse of a variable or constant is called its complement. Since in Boolean algebra, a variable or a constant can have the value 0 or 1, the respective complement will be 1 or 0. You need to note that a binary operator is applied on two operands and unary operator on one. Just as in case of algebra, Boolean algebra also has axioms and theorems. They help us understand the behavior of logical quantities. An axiom is a statement which is considered to be true, whereas theorems require to be proved. The first axiom is the closure property. According to this property, the result of addition or multiplication operations on Boolean variables or constants is always a Boolean value. Let us now learn about the other axioms in Boolean algebra. The identity property or axiom states that sum of any and 0 or product of anything or any value and 1 is same as the original anything or value. Therefore, 0 is the identity in case of addition operations, and 1 is the identity in case of multiplication operation. Thus, we can say that a plus 0 equals a. and A multiplied by 1 is equal to A, where A can be any value. The next property is the commutative property. According to this property, in case of addition or multiplication operations, the order in which the variables are added or multiplied does not change the result or the truth of the expression. Thus, we can say that A plus B is equal to B plus A, and A multiplied by B is equal to B multiplied by A. The next axiom is the distributive law. According to this law, the sum of two variables when multiplied with another variable is equal to the sum of the product of the first and second variables and first and third variables. Thus, A multiplied by the sum of B and C is equal to the sum of A multiplied by B and A multiplied by C. Let us now move on to the next axiom, that is the complement. According to this axiom, when a Boolean quantity is added or multiplied with its complement, the resultant will be the respective identity. Thus, A plus complement of A is equal to its additive identity 1, and A multiplied by complement of A is equal to the multiplicative identity 1. The next important axiom is the law of idempotency. According to this, when a Boolean quantity is added or multiplied to itself, the resultant is the Boolean quantity itself. Thus, we can say that A plus A is equal to A, and A multiplied by A is equal to A, where A is the Boolean quantity. Next, let us learn about the null element axiom. According to this, for any Boolean variable, the sum of the variable and 1 will always be 1. Also, the product of Boolean variable and 0 will always be 0. Thus, A plus 1 is equal to 1, and A multiplied by 0 is 0. The next axiom is the involution axiom. This axiom, complementing a variable twice or any even number of times, results in the original Boolean value. Thus, complement of A complement is A, where A is a Boolean quantity. Let us now move on to learn about associative property. According to this property, the order of grouping the variables while finding the sum or product of the variables does not affect the truth of the expression. Thus, we can say that A plus B plus C in parenthesis is equal to A plus B in parenthesis plus C, and A multiplied by the product of B and C in parenthesis is equal to C multiplied by the product of A and B in parenthesis. The next property is absorption. It is also known as covering, and it has three forms, as you can see on the screen. Let us now move ahead to learn about the De Morgan's theorem. This theorem states that the complement of a sum or product equals the product or sum of the complements. Thus, the complement of the sum of A and B is equal to the product of the complement of A and B, and the complement of the product of A and B is equal to the sum of complement of A and B. Besides the axioms and theorems we have learned so far, there is a principle called the duality principle. According to this principle, starting with Boolean relation, we can devise another Boolean relation in three ways. Firstly, by changing each OR operation to AND. Secondly, by changing each AND operation to OR. And the third way is by complementing the identity elements that is 0 or 1. For example, the dual of relation a plus 1 equals 1 is a multiplied by 0 equals 0. As you notice, the second part of axioms and theorems is actually the result of this principle. Practically, this theorem is enough to prove half the theorem. The rest of the theorem comes from the principle. Let us now compare Boolean algebra with arithmetic algebra. On comparison, we will find that in addition operation can distribute over. But Boolean algebra does not have logical subtraction and logical division, as there is no additive or multiplicative inverse available. However, in Boolean algebra, complement is available. Boolean algebra with two values contains only 0 and 1. Let us now learn about Boolean function. A Boolean function is an expression formed with one or more Boolean variables, Boolean constants, Boolean operators, parentheses, and equal to sign. This will always give out a Boolean value as result, as specified by closure property. We can represent a Boolean expression or function in three ways: algebraic, truth table, and circuit diagram. The axioms and theorems we have learned so far are all examples of algebraic representation. Let us look at some more examples. Consider a function f is equal to a into b, which is formed with two Boolean variables a and b with the operator AND. For a equal to 1 and b equal to 1, this function will be equal to 1, else it will be 0. Let us consider another example, where function p is equal to a into b into c complement. This formed with the help of three Boolean variables a, b, and c with AND operator. This function p will be equal to 1 if a is equal to 1, b is equal to 1, and complement of c is equal to 1, which means c is equal to 0 in all other situations, p will be 0. We can also represent these functions as shown here on the screen. So far, we have seen the examples of simple Boolean functions. However, complex Boolean functions can be formed with the help of simple expressions. Take a look at some complex functions shown on the screen. When an expression or a function has two or more operators, the parenthesis and precedence of operators decides the order of operations. Take a look at the table showing the precedence of Boolean operators moving from high precedence to low precedence. Let us now learn about truth table representation. A truth table is a chart of ones and zeros arranged in such a way that it indicates the results of all possible input options. The number of Boolean variables in a function decides the number of columns in the table. If p is a variable expression, then the table will have 2 raised to the power of p rows. These rows in the table are filled with the help of binary representation of the integers from 0 to 2 raised to the power of p minus 1 in the same order. Let us take a look at how to fill the table for a variable a. As you can see in table 1, there are only 2 rows, since the table is for only one variable, that is, 2 raised to the power of 1 is 2. Next, take a look at the second table shown on the screen. It has 4 rows because it has 2 variables, a and b, based on the same principle, 2 raised to the power of 2, which is equal to 4. Similarly, when the Boolean function has 3 variables, it will have 8 rows, as you can see in Table 3. Now let's see how to represent a simple Boolean function, f of a equal to a complement, with the help of one variable table. As you can see in the table, the second column of the table gives the value of Boolean function, that is, a complement. From this table, we can understand that if a is true, then complement of a will be false, and vice versa. The truth table for the Boolean function, which is applied on 2 variables with all basic Boolean operators, that is, and, or, will be as shown on the screen. Take a look at the screen to find the algebraic representation of some of the functions we have seen earlier using the truth table. By now, you already know that the value of function p will be 1 when a is 1, b is 1, and c is 0, as you can see in Table 1 shown on the screen. As you can see, Table 2 shows the algebraic representation of the function f3. Take a look at the truth table showing the algebraic representation of another function p. Let us now move ahead to prove the various theorems of Boolean algebra. We can prove the theorems in 2 methods. The first is the algebraic method, and the second is using the truth table. In the algebraic method, we use axioms and theorems, just as we do in mathematics. In the truth table method, a truth table is used to prove that the expression given on the LHS, that is, left-hand side, gives the same result as the one on the RHS or right-hand side. This is actually a theorem for verification and not for proving. Let us now move ahead to prove the associative theorem algebraically. According to this theorem, a plus b plus c equals a plus b plus c, and a into b into c equals a into b into c. Take a look at the proof shown on the screen. Also, take a look at the truth table method of proving the theorem. As you can see, LHS is equal to RHS. The theorem is. Let us now move ahead to prove the null element. According to this theorem, a plus 1 is equal to 1, and a multiplied by 0 is equal to 0. Take a look at the algebraic and truth table methods of proving the theorem. As you can see, in the truth table method, LHS is equal to RHS, and hence the theorem is verified. Let us now take a look at the proof for the involution theorem in algebraic method as well as truth table method. As shown here, in the truth table, LHS is equal to RHS. Hence, the theorem is proved. Take a look at the proof for the idempotency law in algebraic method as well as truth table method. According to this law, a plus a is equal to a, and a multiplied by a is equal to a. As you can see in the truth table, LHS is equal to RHS. Hence, the theorem is proved. Let us now move on to prove the absorption law. The first theorem of this law states that a plus a into b equals a, and a into a plus b equals a. Take a look at the proof of this law in algebraic as well as truth table method. The second theorem of this law is stated as shown on the screen. Take a look at the proof of this law in algebraic as well as truth table method. As you can see in the truth table, LHS is equal to RHS. Thus, we can say that the law is verified. Moving ahead to the third theorem of this law. It is given as shown on the screen. Take a look at the proof of this law in algebraic as well as truth table method. Since LHS is equal to RHS in the truth table, the law is verified. Let us now move ahead to prove the De Morgan. The statement for this theorem is as shown here on the screen. Following is the proof for the theorem. Let us now look at the truth table, De Morgan's theorem. Since, based on the truth table, we find that LHS is equal to RHS, De Morgan's theory is established. Thus, we can state that complement of A multiplied by B is equal to complement of A plus complement of B. In this module, you have learnt George Boole, an English mathematician, introduced the concept of Boolean algebra in 1854. Claude Shannon's work on using Boolean algebra to design switching circuits in late 1930s became the foundation of computer logic and design. According to Boolean algebra, things are mapped into bits and bytes. Due to this, we can find its applications in telephone switching circuits, in the hardware and software applications of computers, etc. Boolean algebra is made up of elements, operators, axioms, and theories. Elements are variables or constants with value 1 or 0. The operators in Boolean algebra are and, or, and not. According to closure property, the result of addition or multiplication operations, plus or addition or multiplication on Boolean variables or constants is always a Boolean value. The identity property or axiom states that sum of anything or any value and 0, product of anything or any value and 1 is same as the original anything or value. Commutative property A plus B is equal to B plus A and A multiplied by B is equal to B multiplied by A. Distributive law A into the sum of B plus C is equal to A into B plus A into C. Complement A plus complement of A is equal to 1 and A into complement of A is equal to 0. De Morgan's theorem states that the complement of a sum or product equals the product or sum of the complements. Thus, complement of the sum of A and B is equal to complement of A into complement of B, and complement of A into B is equal to complement of A plus complement of B. We can represent a Boolean expression or function in 3 ways: algebraic, truth table, circuit diagram. A truth table is a chart of ones and zeros arranged in such a way that it indicates the results of all possible input options.